Okay, we're extremely happy to have here with us today Wolfgang. Um, Wolfgang. I've completely forgotten everything by now, due to various deadlines. So, and from Freie Universität Berlin. So, and he is going to tell us some stories about disk graphs and transmission graphs.
Exactly. Yeah, thanks, Boris, for the introduction, and thanks a lot for inviting me and for coming to my talk, even now 2 days before the sausage deadline, right? So in case you haven't missed it, so the sausage deadline has been moved by 1 day, so you can relax and listen to the talk. Yeah, sorry for the short notice change of my talk title. That also has to do with the sausage deadline that we discovered a hole in the other result I wanted to present, so that now I will talk about something else. So the talk therefore is a bit improvised. It has some old parts and some new parts. And so I hope you will like it anyway. And so I will talk about robust algorithms for finding triangles and computing the girth in disk graphs and transmission graphs. And so the talk will have two parts. So first I will just talk about triangles and the girth in disk graphs and transmission graphs. And then I will talk about robust algorithms, what they are, and how they come into play. But now we just talk about disk graphs and transmission graphs, and let me try to remind you, in case you have forgotten or you've never seen it, what a disk graph is. So a disk graph is a geometric intersection graph. They're defined in the plane. We have n points in the plane, and in that context, we usually call them sides. And each side has an associated radius. So with each side, we associate a number Rp, which is just a rational real number larger than 1, and this we interpret as a radius, and then we draw a circle around each or a disk around each side with that radius, and this gives an arrangement of disks. And now I can define a graph on that adjacent if and only if the disks that are defined by the respective radii intersect, or in other words, if the distance is at most Rp plus Rq. And this gives us a graph, and this graph we call disk graph. And so we very much like these graphs because they are very simple, they have nice structure, they're very general, they occur a lot in practice, like sensor networks, or if you have transmission stations. And so they are very interesting to study. And so now, like any question that you can ask for a general graph, you can also ask for disk graphs, and then you can ask whether this question can be answered more easily or more quickly on a disk graph than on a general graph. And so now let me talk about the question that I am interested in this talk. And the general question that I'm interested in is determining the girth of a graph. And what is a girth? A girth is the following concept. So this holds for any graph, not just for disk graphs. Basically, what we have is we are given just a simple graph, and what we want to know is the length of the shortest cycle in the graph, or the shortest cycle itself. It depends on what we're interested in. And so the length of the shortest cycle is called the girth. And for now, I measure the length of the cycle just in the number of edges. But you could also define length for the edges, and then the girth would be the cycle which has the minimum total length. But for now, there's number of edges. And for example, in this graph, I think the girth would be 4, if I'm not mistaken, and the shortest cycle would be this one here. And I think it's unique. And then in particular, a particular instance of this question is there a question or no? And a particular instance of this question is checking whether a graph.
There seem to be other cycles of length 4.
Oh, are there? So oh, this one here. Oh yeah.
Three
so there's one to the right. Thank you.
And there's one in the middle.
Oh, very good, very good. So it's not unique. Thank you. So, but there's no circle of length 3. Very good. Thank you for paying attention. So I was too optimistic, but so yeah, so there's 2 more. Thank you. And so I think one particular instance of this question of determining the girth of a graph is the question whether a graph contains a triangle the cycle of length 3 or a clique of size 3? And this is a classic question, and it's a very hard question that has been studied a lot. So let me tell you what's known about this. So I think the best known algorithm for general graphs, the best known algorithm for general graphs to compute the girth and also to determine whether a general graph contains a triangle has running time n to the omega, where omega is the fast matrix multiplication constant. I think so the number here is slightly dated, so I think the matrix multiplication constant has a bit been improved since these slides were made, but I don't know exactly, but now maybe I think it's 2.371 something, but I don't know. And so this is an algebraic algorithm that uses a fast matrix multiplication. And if you do not allow fast matrix multiplication, if you insist on the combinatorial algorithm, whatever that means, we don't quite know what that means, but some people say, okay, I recognize it when I see it. So if you try to focus on combinatorial algorithms, then actually you can do slightly better than the naive algorithm. So the naive algorithm would, at least if you want to check for triangles, would be just to check every triple. And for computing the girth, basically you have to do some all pair shortest path computation. But so the best combinatorial algorithm is I think due to U, and it gives and basically n to the third over some polylog, log n to the fourth is the current best result as far as I know. And there's also, but that's the combinatorial algorithm not using fast matrix multiplication. And then there's also approximations. So if you want to just have an additive +1 approximation, you can improve from n cubed to n squared. And then there's also a lot of work on this, in particular the question of whether a graph contains a triangle has been studied a lot, and it's one of those hardness assumptions that we believe, or I mean, at least people like to conjecture that there's no combinatorial algorithm for finding triangles that is truly subcubic, I think. And so that makes this problem interesting. So it has a lot of history. And now, I mean, what I told you is for general graphs, but for planar graphs, we can do much better. For planar graphs, the girth of a planar graph can be determined in linear time as opposed to cubic time. So that's much better. And then the question that we can ask is, what about disk graphs? Are disk graphs more like or disk graphs more like general graphs? And so typically there's two answers that you can give. On the one hand, you can say, of course, disk graphs, they're completely different than planar graphs because, I mean, they can be very dense, they can have large cliques and so on. But on the other hand, you can say, well, but they're in the plane, they have some geometry, and this geometry can be exploited, and so maybe they're more like planar graphs. And the experience shows, at least for many results, disk graphs are more like planar graphs. So if you have a good algorithm for a planar graph, you can also have a good algorithm for a disk graph. So, and that's the question that I want to address now. And so let's see, what can we do about disk graphs? Does the geometry help? And in fact, so it turns out that there's some very nice, at least I think, very nice, very clean, very beautiful way of solving this problem for disk graphs. And once you see the right lemmas, I think it looks very easy, but of course you first have to find the right lemma. And so here's one interesting fact about disk graphs that we can use. And let's look at the following lemma. It says we have some disk graph G, and let's assume that this graph is not plane. That means so a disk graph or embedding, right? So because the disk graph is defined by points and disks in the plane. And so now I just draw the edges geometrically as straight lines. If there's an edge between two disks, I draw a straight line between them, a line segment, and otherwise not. And then I get an embedded graph, a geometric graph in the plane. And if this graph is not plane, that is, if there are two edges that cross, then actually you can prove if this happens, then there have to be three disks in the disk graph that intersect in a common point. So that's some simple geometric fact. which was, we discovered it, but it was actually also known before we discovered it. So when we looked in the literature, we also found somebody else who proved it. And so it's actually not so hard to prove, but it's a bit annoying, some case analysis. Here I show you an example. So here's a disk graph. I hope I didn't forget any edges. And the edges drawn as straight lines, as line segments. And here we see it's not plane because there exists an intersection. And then we see actually, so there have to be 3 disks that have a common point, actually this intersection point in this case. And why is it interesting for us? Well, these 3 disks that intersect in a common point means these 3 disks intersect each other, and it means that the disk graph contains a triangle. So if a disk graph is not plane, then necessarily it has to contain a triangle, and it means necessarily it must have girth 3.
This
so
graph
now
actually is plane, I think, Wolfgang.
Is it plane?
Yeah, because
So-
that edge shouldn't be there.
According to his
Ooh.
definition, he allows crossings even though the graph globally is a plane graph.
Oh, but you're saying,
it can
you're
be
saying, I'm sorry.
redrawn.
Yes, I'm sorry. I think what you're saying is that this picture is not good because these 2 disks, they look like they're disjoint, right?
Right.
So I didn't draw the disc right. Thank you. Yes. Thanks for pointing it out. Yes. So my picture is slightly wrong. So the discs touch, but they should be a bit bigger. So imagine this lower disc being a bit bigger. I'm sorry. So that's a mistake in my picture. Yes. Thank you. So let's imagine this the disc down here. The lowest disc is a bit larger than I drew it, or maybe it moved down a little bit when I changed the picture. Thanks for pointing it out. Yes, I have to fix that.
I have another question, Wolfgang. Is
Yeah.
it possible that you actually get 4 disks intersecting in this case?
I think
if you have 2 edges that intersect, it seems like you actually get 4 disks overlapping.
That's not
Is it-
true. That's
No?
not true.
it would surprise me.
Maybe for unity, so I don't know what for if do you allow arbitrary radii?
I allow, so this holds for arbitrary disks.
You're right.
So yeah, in
you're
this
right.
picture I drew unit disks, but it holds for arbitrary disks. Yes.
Yeah. For unit
Um,
disks, I think you actually get 4.
Thank you. Yes. I think for general it's only 3, but this holds for arbitrary.
So by the way, Wolfgang, this lemma, as Micha Sharir always like to say, has been known probably to the Greeks. And
So my reference is not old enough. Yes.
it is in fact true for pseudodisks. Right.
Okay. Very good.
So
Yeah.
so it's very general.
So you have an older reference for it, Shachar, or it's just everybody knows?
I mean, it's the counterpositive, right? It means that if no point belongs to 3 disks, so at most 2, you want to say
Yeah.
that it is planar. This is true even for pseudodisk, and it was basically shown in this 86 paper by Kedem Livne Pach Sharir about the union complexity of but I can show you a very simple, like, 1-line proof of that
very good.
For this, for pseudodisk, you need this. I don't know. It's one I can give you references later.
Oh, thank you.
I
So
also
that's
use it in a
interesting.
paper. No.
So very good. So it's one of these things that everybody rediscovers, and apparently, yes, a very nice fact. Okay, good. So thanks, Shachar, for the reference. Okay, so and I will update the reference. Yeah. So the consequence. So as Shachar also said, what we are interested in is so either a disk graph is plane or it has girth 3. And now everything becomes very easy. So we have a disk graph, but actually, so our input to the algorithm is just a set of points in the plane and the radii for each. And then the first thing that the radius for each point. So that's our input. It's compact. It has a linear size linear and the number of sides. And then the first thing that we do is we construct a disk graph just using your favorite sweep line algorithm. So that we know what the edges are. And actually, during the sweep line algorithm, we can also check whether there are 2 edges that cross or not. And if we have two edges that cross, then we can report that there's a girth, that the graph has girth 3, and actually we find the triangle, we can report the triangle. If not, we know that the graph is plane, and then we can just use known results for planar graphs. And the resulting running time that we get is, well, for the algorithm for planar graphs, it takes linear time, as I mentioned. So the running time is dominated by the sweep-line algorithm. And the sweep-line algorithm, it basically, the main operation that you need is to sort the points from left to right and to maintain a priority, not a priority queue, just a sorted order, like a tree on the points. And so that takes n log n time. And actually, this is optimal. So in the algebraic decision tree model, you can also improve an according lower bound. So that's very nice because it shows that we can improve this running time for general graphs from n to the matrix multiplication to n log n. But actually, it's not quite like planar graphs because we have this n log n factor. Okay.
What is the, when you say use algorithm for planar graph, you mean algorithm for girth in planar graphs?
Yes, for girth and planar graphs. So that's basically, I mentioned it here. So basically this graph down here that I cited by Chang and Lu from 2013, which uses linear time.
Okay. So why is it, so why do you need n log n? I don't understand.
So the input is not the graph, but the input is points and radii. Right, so the input just says you have a set of points in the plane, and for each point an associated radius.
And you're saying that at least to construct the graph you need n log n?
You need to construct the disk graph, but actually you're not constructing the disk graph. So you are constructing the disk graph partially, right? So you start constructing the disk graph, and either while you construct the disk graph, you discover two edges that cross, and then you immediately abort your construction of the disk graph, and you report a triangle, the triangle that you found when the edges cross. Or the construction finishes without finding two crossing edges. Then you know that your disk graph is plane. So in particular, also the edges, the number of edges that you constructed is linear. And then you have a planar graph, and then you throw away the geometry and you just use the algorithm for abstract planar graphs.
So it's funny, but it seems that if you were just given the graph abstractly, it would be easier than that if you are given the
I will talk about that. So that's the robust part. I mean, so that's basically the old part, and then we will talk about the situation for abstract graphs. Actually, also interesting.
Okay.
The new part, right? So, but so you're already going in the right direction. So I'm glad you're following the way. We go to that. Let's just take a small detour. So maybe one thing that's also interesting. So now I talked about the unweighted case, but actually, so this idea that we had that you can also generalize it to find the shortest triangle. So now the question is slightly different. So now again, we have a disk graph. And so when I say we're given a disk graph, as I said, you don't really have the graph explicitly, but it's given implicitly by a point set and by associated radii. And now the edges have weights. So the length of an edge is just the Euclidean length, the distance between the endpoints. And what we want to do is we want to find a triangle in this graph. But not any triangle, but the shortest triangle, so that minimizes the total length. And again, we want to do that and faster. So in this example, but of course, in spotting these things, I think that could be the shortest triangle, but maybe somebody has a good eye and thinks that can argue that another triangle is shorter. I'm not sure, but maybe this one is the shortest triangle. And so the way we solve it is basically we first solve the decision problem, and then we use not parametric search, but chance optimization technique because it's somehow easier, or at least conceptually nicer than parametric search, because also do that. But so basically what we want to do is we just want to solve the decision problem. So we're given some number, and the question is, does our graph not just contain a triangle, but does it contain a triangle of length W? And so now, given what we already talked about, it's actually not so difficult to solve this problem. So let me just tell you, just because I think it also tells you some things that typically you can do when you work on disk graphs. Of each grid cell is W over 3, where W is our parameter where we should decide whether there exists a triangle of total length at most W or not. And then what do we do next? Now we look at each grid cell and we look at the disks whose centers only lie in that grid cell. So for each grid cell, we check that. And now the first thing that we can do is we can use the algorithm that we already have, the decision algorithm, whether a disk graph contains any triangle. And we use that separately in each disk cell. Yeah. And this takes n log n over overall, and we know if there's like one of the subgraphs, one of the induced subgraphs in whose sides are all in one cell of the grid cell contain a triangle necessarily, because the diameter of this grid cell is at most is W over 3. The length of the triangle has to be at most W. We are done. So we know now. So either because we find a triangle inside the grid cell, or so in this case we would be done, or we know that each grid cell does not contain a triangle, or no grid cell contains a triangle. So that means the induced subgraph in each triangle is plane. And now we know also the triangle has to go between neighboring grid cells. And so now somehow basically you can use these texts that basically inside each grid cell there have to be few edges. It has to be sparse, and we know that the triangles, if they are there of length at most W, they have to be somehow local. They can only go between grid cells that are close together, maybe one or two apart. Then there's very few candidate triangles that we need to check. We do check them, and then either we find it or we know it does not exist. And so then if we work out the details, you can log n time, and then there's some general hours to go from the decision version to the optimization version, and then we're done. Okay, so I think that concludes the geometric part. And now I want to switch gears. I want to talk about this robust thing. So now I go to the second part of my talk, and here we see that my talk is a bit improvised because now I'm switching slides. And so I'm sorry for that. I didn't have time to make it all uniform because of the short notice. But now I go to the robust part, and I also talk about transmission graphs. And so let's talk about that. And and I also have to say what robust means, and I also introduce some new characters into my talk called transmission graphs. So here we saw already disk graphs. Unit disk graphs are just graphs where disk graphs where all the disks have radius 1, as you know. General disk graphs we saw, and there's transmission graphs. Transmission graphs are a directed version of disk graphs, where again we have a set of sides and radii associated with them, but now the edges are directed, and there's some edge from a side U to a side V if the side V is contained in the disk of radius RU around U, right? So each side has a disk, and now I have the center of one disk to all the sides that lie inside this disk. So this is really, you have like some broadcasting towers, and they can send in one direction, and you can reach everything that is within your transmission range. But then it can be like the other, the point that's inside transmission range is still power, but it's somewhat weaker, and so it cannot reach you back. That's what here. These are transmission graphs. And I will also introduce them and use them for this talk. And now we go to a different setting. So far, what I talked about was the setting that the input graph is given geometrically. So the input is a unit disk graph, but the unit disk graph is really represented by a realization. So that means you have the point radii. And now we look at the situation that my input is an abstract graph, really, and let's say an adjacency list representation. So I have the graph, I have the vertices and the edges, but I do not have the geometry. I just have the graph, as Shachar also already asked. And now it's a bit tricky because now we are given this graph, and it might be a disk graph or a unit disk graph, or it might not be. We don't know. And but we want to use like some of these ideas. We might use some of these ideas that turned out to be useful for unit disk graphs in the geometric setting to this abstract setting. But we don't know, is this graph that we're given, is it really a disk graph or not? And there's different ways how to deal with that. And I mean, so the situation for planar graphs is easy because for a planar graph, we're just given an abstract graph. But if you're not sure if it's a planar graph or not, there exist efficient algorithms that check whether a given abstract graph is a planar graph, as you probably all know, right? So you can do is a graph a planar graph. You can check planarity testing is one of the oldest problems for which efficient algorithms exist. And so it doesn't really matter. So you can check that. But for disk graphs, that's not the case. So we don't know if there's an efficient algorithm for checking whether a given abstract graph is a unit disk graph or a disk graph, or if it's directed transmission graph. And we believe that it's not the case because these problems are known to be hard for the existential theory of the reals. So this is not clear if you're given an abstract graph, whether you know whether it's a disk graph or not, and you really don't have an efficient way of checking it. And now, how can you deal with it? One way is you just say you're in the promise setting. You say, okay, I just assume the graph that I'm given is a disk graph. And if the graph that I'm given is a disk graph, then my algorithm will be correct and will do what it's supposed to do. And if the graph is not a disk graph, then there's no guarantees whatsoever. The algorithm may do anything. I don't care, right? That's called the promise setting. So I just assume there's some property that my input has to have for the algorithm to work. And I cannot really check this property. And so I just assume this property is there. And if not, then I don't care. That's called the promise setting. And now there's a different way. And that's called the robust setting. And this robust setting we didn't invent, but it was invented by Ragavan and Spinrad actually more than 20 years ago in 2003, also for the setting of unit disk graphs. And the robust setting says the following. It says the input. So let's say, again, I want my input to have a certain property. I don't know how to check this property efficiently. And I want to have some algorithm that works well for inputs that have this property. And in the robust setting, again, like in the promise setting, if the input has the property that I'm interested in, then my algorithm should work. But what happens if the input is not in the domain? Then again, there's some guarantee, and there's two guarantees. So for some inputs that are not in the domain, it might still be the case that the algorithm works. So the algorithm will do whatever it's supposed to do, and it will give me the correct answer. Or the algorithm will realize at some point that the promise is not fulfilled, the property that the algorithm needs is not fulfilled, and then the algorithm will answer correctly that the input does not have the property that that the algorithm requires. But I have a guarantee. So there's always a guarantee. Also, if they're not in the domain, either I get an answer, and if I get an answer, the answer will be correct. And if I do not get an answer, then the algorithm will be correct in telling me that the reason why I do not get the answer is that the property that I need is not fulfilled. Yeah, does it make sense to get this definition? And yeah. And yeah, as I said, now what we want to do is we want to go from the geometric setting that I showed you to the robust setting. And so the reason why it's interesting for unit disk graphs, but it's, for example, not interesting for planar graphs, is that this property of checking whether a graph is a unit disk graph or a disk graph or a transmission graph, all these properties are hard for or complete for the theory of the reals. And so the existential theory of the reals is something that lies in P space, but probably outside NP. Okay, so does it make sense? Do you get this definition, or should I get more? Okay, super clear. Okay, and so now again, let's look at the problems that we're interested in. So we're looking at the problems of triangle detection and computing the girth. And so I showed you already how triangle detection in disk graphs can be done in n log n time. And actually also for transmission graphs, I did not show you that it can also be done in n log n time, but that's a bit more complicated. And now what I will show you actually that finding a triangle in a unit disk graph can be done in linear time. So so as Schacher pointed out, it's easier probably in the robust setting, and for unit disk graphs, it's actually the case, and it's very easy. We will see. I mean, it's a very nice and easy trick. Maybe it's an exercise, I don't know, to solve it. And I will also show you that for transmission graphs, you can do it you can find a triangle in linear time, but here you also need the number of edges. So I don't know how to avoid the number of edges. So here actually, so the algorithm for a unit disk graph, it does not need to look at all the edges, but for transmission graphs, I don't know how to avoid looking at all the edges. And computing the girth, so we know for general disk graphs, again, I showed you that this can be done in n log n time. And in the robust setting, I will show you that computing the girth for unit disk graphs takes linear time. And yeah, that's all that I wanted to show you today. Okay, so let's talk about this, how this works. So let's first talk about triangle detection in unit disk graphs. And I promise you this is a very easy algorithm. You can tell it to your students or to your 4-year-old children. I think it shows very nicely this whole setting of robust algorithms and how you can use it also in this setting. And maybe I should say that Dagavan and Spindler, when they introduced these robust algorithms, they were interested in properties or in algorithms that solve problems that are NP hard for general graphs and polynomial time for disk graphs. And so the goal for them was to find an algorithm that runs in polynomial time for disk graphs and some other graphs. And here really we want to we are more fine-grained and we want to find a good running time. Okay, so triangle detection in unit disk graphs. And so what we need is basically we need to identify the property of a unit disk graph that really is needed to find triangles quickly in unit disk graphs. So that's what we need. I mean, so the property of being a unit disk graph is something that we cannot really check. But actually, for the problem that we're interested in, triangle detection, it's the property of being a unit disk graph is not the property that's decisive, but is a property that all unit disk graphs have. That's important, but also some graphs that are not unit disk graphs can have this property, and it would still be good. And so, what is the property that we need? Well, basically, the property that we need is that in a unit disk graph, if you have a vertex and this vertex has at least 6 neighbors, then you can know that this vertex needs to make a triangle with 2 of these 6 neighbors, right? So I mean, it's a simple geometric property, the kissing property, where I mean, so and basically it tells you if you're trying to draw a unit disk graph and you have some vertex of degree at least 6, then the best way you can do it is this. And the way we define unit disk graphs, if the unit disks touch, then there's also an edge. And so if you have at least 6 neighbors, then you have the property that among any 6 neighbors, so among any subset of exactly 6 neighbors, you will find a triangle with V. That's the geometric property that we need. Yeah, that's very easy. I think everybody knows that. And now the algorithm is very simple, actually, and it does not need any geometry anymore. It just needs this property. And this we can exploit combinatorially, right? And so basically our algorithm just checks two cases. And the first case says, okay, I look at the abstract graph that I'm given. I look at all the vertices and all the neighbors. And if all vertices in my abstract graph have degree at most 6, then I just can brute force it, right? So basically then for each vertex, I can look at all pairs of its at most 6 neighbors, and I can check, is there a triangle, yes or no? And this will take linear time, done, right? So here I look at every vertex, I look at all the neighbors, and for example here, at all pairs of neighbors, and here I find a triangle, and this will be easy because each vertex only has constant degree. We can just do that brute force. Otherwise, we do have a vertex of degree at least 6. So for example, here we have a vertex of degree at least 6. And now what we do is we go to this vertex and we pick 6 neighbors. Any 6 neighbors will be okay. We just pick some 6 neighbors. And then for these 6 neighbors, again, we check explicitly for each pair of neighbors whether there is an edge between them or not. And we know if our graph is actually a unit disk graph. So if this graph, this abstract graph we're given, comes from a unit disk graph, then there has to be a triangle. We have to be able to find a triangle. The geometry forces this. So in the unit disk graph, we will find this triangle. And but it may be that in our input graph, we do not find it. So and if we do find this triangle, we're happy and we report it. But it may be that in our input graph, we do not find this triangle because we don't know what it is. But maybe we don't find it. But then we can conclude it's not a unit disk graph. So we can just report the graph that we're given is not this graph, done, right? And so in this way we get around this fact that unit disk graphs, the property of being a unit disk graph cannot be checked in polynomial time because we don't need this property actually of exactly being a unit disk graph. We just need this property given by this lemma, and that's much more easy to check. Okay, and so that's basically the idea of robust algorithms. And I think this illustrates it very nicely. And now, of course, you can try to play this game again and make it a bit more complicated or a bit more challenging. And for that,
so why do you restrict yourself to unit disk graph? I mean, this algorithm would not work for arbitrary disks, not just unit.
I mean, for
I guess the
you don't have
to
this
have the
property
order of the radii or not.
You don't know the order of the radii, right? So I mean, you're saying you just pick the one with the shortest radius or something like that. But I mean, it's not as easy.
If I had a number which are with the vertices which correspond to the radii, I would have been able to do it, right?
Yes, but I don't.
So that's
yes,
the core,
I agree.
That's the core problem, that I don't have the...
Yes. The core problem is I don't have the geometry. I mean, I know maybe there's some geometry, some underlying geometry or not, and but I don't have it. And so then in a disk graph, you cannot say if you have some vertex of degree at least 6, I can pick any 6 neighbors and there will be a triangle, because I might have
bigger. But it's true
I need to have 6 bigger ones. Yes,
yeah.
That's true. I would have to somehow guess an order. So if I find a way of guessing in which one is the smallest, then I could do it. But if not, it's not so easy.
You don't even need the order. You don't need the order. All you need is that for every vertex, we'll find 6 guys that are larger, 6 neighbors that are.
Yes. I mean, I'm not saying it's impossible, and I mean, we do have, but nothing that really runs in linear time. For that, we can do it in n+m time, which is not in this talk. So, I mean, we can do still something, but I think it's not as easy and clean as in that case.
But n log n, you're saying n log n is not interesting? I mean, or you don't have the...
N log n would also be interesting, but I just don't know.
But you don't have anything. You just have the graph. Okay.
Yeah. But still, you can say something, right? So at least for unit disk graphs, and this easy, I mean, maybe now you see it. I mean, I like this because it's very easy, but it really illustrates this kind of idea that you can still say something, even if you just have the graph, but you know it has to be, and you don't know, but I mean, you can say it works if the graph is a unit disk graph, and if not, it may work or it may not work. But
By the way, this property is also true for pseudodisk graph. So there is an order on pseudodisk such that you have this property with not 6, but let's say 300 or something.
That's still fine.
There is a paper that says that every set of pseudodisk has a small pseudodisk.
Very good. Thank you.
Okay.
Yeah, but I also wanted to show you how you can do it in transmission graphs. So how can you find a triangle in the transmission graph? So maybe that's also nice. So now we have a, because there exactly we have this problem of I mean, a transmission graph, but now that's a general transmission graph. So the transmission graphs are only interesting if the radii are different. So, but now let's look at transmission graphs just to have a second example of this. And what I want to do is now I want to find a triangle in a transmission graph, and by a triangle I mean a directed triangle. So it's there's some a circle. Now the edges are directed, and so there's a circle where all the edges are in the same order. And now I want to find a triangle in a transmission graph. And for this, let me first.
What does it mean, a directed triangle? Like a cycle? A directed
Yes,
cycle?
a cycle. Yes, a directed cycle. So a directed cycle of length 3.
Okay.
Yes. Okay. And so for that, let me just define some notions. So now we have a transmission graph. And now for a vertex, I define the incoming neighbors to be n in. So the incoming neighbors are all the sites for which there exists one edge that points into the vertex V. The outgoing neighbors are those where there exists an edge that goes out of V. And then there's the bidirectional neighbors where both I have an incoming and an outgoing edge. So here in the picture, I have 2 bidirectional neighbors, 2 neighbors that are only incoming and 2 neighbors that are only outgoing. Okay. And now I have this lemma. So basically a generalization of what I showed you for unit disk graphs. So if there's a vertex that has at least 6 bidirected neighbors, then there's 2 among these 6. So then I can pick any 6 of those bidirected neighbors and pick 2 of them, and there will be a directed triangle there. So it's again a kind of a similar argument as not as simple as with the kissing property, but you have to have some cones, and then you can show that. So if you look at these bidirected neighbors, then you get a similar property. And there's a second property that we need for transmission graphs. And the second property is that if you look at a directed cycle in a transmission graph, then every directed cycle in a transmission graph has to have at least one bidirectional edge. And so, for example, here there's a directed cycle in a transmission graph. And what happens is, so as Shachar said, you do have basically some order, which is induced by the length of the disks or the size of the disks. And if you just look at a directed cycle and you look at the smallest disk in the cycle, then the smallest disk, the outgoing edge from the smallest disk in the cycle, there has to be an incoming partner, because then the other disk from the outgoing neighbor, it has to be at least as large as the disk from the smallest disk, and then there also has to be an edge in the other direction. And that's basically the way how we can find the smallest. So that's somehow a way how we can identify, even if we have only an abstract graph, an abstract transmission graph, how we can identify this the smallest disk.
But isn't it true just for every connected component? Like every connected component of the graph, if you ignore the direction, it has one of the edges is in fact bidirectional, isn't it?
Yes, I agree. Yes, it's just the smallest. Yes,
has nothing to do with cycles.
No, not. It's just that's what interests us. No. Okay. And so now there's what we need is still some algorithmic lemma, which tells us that so now the game is somehow we're given this as a graph, and we have to identify these bidirectional neighbors. And so for this we have the adjacency list representation. And we assume that our graph is given in the adjacency list representation just completely abstractly, and in a directed adjacency list representation. And then there's like a simple algorithmic lemma. It's a bit tricky, or I don't know if it's tricky. It's an exercise that you can identify the set of all bidirectional neighbors in n plus m time, so in linear time, by a few scans over the adjacency list. And so the idea is that you have to do some kind of so you have to sort these adjacency lists basically so that they're, I mean, basically what you want to do is you want to have some order on the vertices so that all the adjacency lists are given in the same order, all the adjacency lists are sorted according to this order, and then you can just find the bidirectional vertices by edges by merging. But so to impose this order on the adjacency lists, you have to do some kind of tricks, like you go through the adjacency lists and you sort them twice and you transpose them, and then you get this. But I don't want to go into details, but it's something you can do. And now that we have all these ingredients, I can tell you how to find a triangle in a transmission graph. So the first thing that we do is we have the adjacency lists of these ordered adjacency lists or of the transmission graph, or of of some directed graph, which may be a transmission graph or not. And the first thing that we do is for each vertex, we compute the bidirectional neighbors using this merging of the adjacency lists tricks and transposing trick in linear time, in time n plus m. And then basically we do what I showed. So either it is the case that for each vertex, the number of bidirectional neighbors is at most 6. And in that case, what we do is we delete all the bidirectional neighbors from the graph. And then the resulting graph has to be acyclic, because we know that in every transmission graph, in every cycle, there has to be, and so there seems to be a mistake. So some directed cycles survived, so in every transmission graph, so in every transmission graph, in every cycle there has to be one bidirectional edge. So if I remove all the bidirectional edges from my graph, the resulting graph has to be DAG. And if the graph that we get is not a DAG, then the resulting graph is not a transmission graph. So the input graph is not a transmission graph, and we can show that we can just report that the input graph is not a transmission graph. So that's one way how we can detect our input graph is not a transmission graph. We remove all the bidirectional edges and see that the resulting graph is not acyclic. And otherwise, we check for every edge that has some bidirectional neighbor. We can check explicitly if it closes a cycle, or if it is contained in a cycle with length. Okay, and this again takes n plus m time, if I remember correctly. Otherwise, the second property that we use is the one that I mentioned. So if we have a vertex with at least 6 neighbors, then if we with 6 bidirectional neighbors, then we can take any 6 of them, and we can check there explicitly for a directed triangle. So we just need to see whether there's some additional edge. And yeah. And if we do not find such a triangle, then we again can report that the graph is not a transmission. Yeah, so this basically these ideas that worked for unit disk graphs, they also work for in the directed case for transmission graphs, but it gets a little bit more involved. So you need to do some additional tricks. And I think that's I think, and like a third bonus result. So actually, we can also generalize this for computing the girth in a unit disk graph. I mean, so basically the same tricks that I showed you, you can also use it for a robust algorithm that can compute the girth of a unit disk graph. Again, using this this lemma that I already showed you. If a unit disk graph has no triangle, then it's planar. So what we can do now for, so here's again visualize. And so now, how do we do it? So first we use just our result for checking whether there's a triangle in this graph. If yes, then we know that the girth will be 3. Otherwise, we still have this abstract graph, and we know this abstract graph does not have a triangle, and we know it may be a unit disk graph or it may not be a unit disk graph, but so far we have not discovered that it's not a unit disk graph. And so the next thing is we can just check whether this graph is planar in linear time. If no, then we know we have a graph that does not contain a triangle and that is not planar, then it certainly is not a unit disk graph. Again, we can say it's not a unit disk graph, or again, it's a planar graph. And then we can, and actually every planar graph is also a unit disk graph, and we can just use the girth algorithm and solve the problem in linear time. So again, even in the abstract setting, in the robust setting, we can check in linear time, and we can compute the girth of the graph. Okay, and I think that's all that I wanted to show you. So now I showed you some problems on disk graphs. I showed it for the geometric setting. These were old results, just as some kind of motivation. And then the new part was that these algorithms can also be made robust in the sense that we don't have the geometry, but just some abstract graph, but we can use the properties of the geometry to speed this up. And I mean, so here it still says that we're looking for an efficient, robust algorithm for general disk graphs. So that we found, so we can also find triangles in general disk graphs in time O of n plus m. And but we don't have an efficient, robust algorithm for the Gaussian transmission graphs yet. And I think that's all that I wanted to show you. Let's see, how am I doing time-wise? Okay, I think, yeah.